Very welcome to all of you, and we have already talked about particle in an infinite potential well, and today we would like to extend the same idea, we would like to move on with the same idea, but now the particle will be facing a finite potential. So how will it look like when we talk about the particle which is in a finite potential? Now, if I go back to the previous talk, we had the particle in an infinite potential. And it was impossible for the particle to leave the potential. It was a pure hypothetical experiment. And we could realize that this infinite potential that we have, what it does basically, it dictates the particle. It dictates the particle to have some finite energies. It dictates the particle to be wired in that infinite potential. And there is no restriction on the number of energies that the particle can have. It can have infinite number of energy states, but all of these energy states are dictated by the potential well. Obviously, it is a symmetrical problem. Now, we have the same story for the same particle in the same type of one-dimensional box, but now the potential that it will feel is finite. So, what do we expect now? We will not expect infinite energy states in which this particle can be. But at the same time, we will see that the particle in this finite potential well, the point is that this particle, whom I call a quanta, this particle has energy less than that of this finite potential. So, if I say that this particle has less energy than that of the finite potential, then classical physics has a complete answer for this particle. The classical physics tells you that it's not going to cross this barrier, because we are assuming that this particle has energy less than that of the potential barrier. But when we see the same problem in the framework of quantum mechanics, the particle does not behave like a particle. The particle is not assumed to be a particle. It is assumed to be carrying a wave function. And if it is assumed to be carrying a wave function, the wave function has a property of spreading. So, when I talk about the particle in a one-dimensional box, I can think about this particle as a spread of disturbance in the box. And this spread gives this particle a chance, even though that chance might be very, very less, a chance to escape this finite potential. Are you getting my point? Okay. So, your particle in same geometry but with finite potential. At the same time, this particle has zero potential energy inside the box, and it's carrying a finite potential outside the box. Right? So now we are trying to understand that will this particle have some framework of probability that it can cross this barrier, because classically, it is impossible for this particle to lose this barrier, right? And our problem is symmetrical in nature. There is a perfect symmetry in this. And obviously, you can expect the solution in terms of odd and even functions. As I have already described, the true nature, the imaginal nature of odd functions and even functions. We have already tried to understand that how does these even and odd functions look like, and how does they ensure the symmetry in terms of their probabilities in the one-dimensional box. So what we have here, what we have is we have this particle in this one-dimensional box. Inside this box, the potential is zero. There is no potential. The particle has only kinetic energy inside the box. And now this potential is finite, and it is finite outside in the left, and it is finite outside in the right. And now the potential will dictate this particle. But if this particle has a desire, if this particle has a desire to escape this potential, can this particle leave this potential quantum mechanically? This is what we are trying to understand. Will there be any probability for this particle to be on the other side of the potential, even though the potential is finite? But at the same time, this potential is greater than that of the total energy of the particle that is inside this one-dimensional box. Is this clear? So what we can do is, we can, in order to make this problem symmetrical, we can choose from minus L by 2 to plus L by 2. Okay? So here x is less than, if you want to move here, x is less than L by 2, and here, if you want to move in this region, x is greater than L by 2. Right? Now what you have? You have a wave function basically existing inside this box, whom we are calling a particle, right? But this wave function is representing this particle, right? So what we have here, we have a region with finite potential such that this potential is greater than that of the total energy of the particle, right? So if I divide this problem, I can divide this problem into the three parts. You can have the part 1, and you can have the part 2, and then you can have the part 3. Right? Okay? So we can realize this problem in three domains, in three frameworks. What am I trying to tell you is, I'm trying to tell you that if we have to have an acceptable eigenfunction, it must carry certain properties with it. The first important property is that it must be continuous. It must be continuous. Now think about this. That means if I have the particle, if I have to define, if I have to connect this region with this region, the eigenfunction of this region, if I call this psi 1, must be equal to the eigenfunction of this region at what point? At x equals minus L by 2. Because you want to make the connection, right? So psi has to be continuous. It has to be continuous at this point. Inside it is continuous. There's no problem. Its derivative is continuous. There's no problem. But at the boundary, to make the problem plausible, you want the continuity. So if you want the continuity, you will think about the boundary condition. And the boundary condition will be what? It will be that psi 1 of x must be equal to psi 2 of x. But where? At x is equal to minus L by 2. Are you getting my point? At the same time, if the eigenfunction is continuous in space, then its derivative must also be continuous in the space. Right? So that boundary condition, so you will be using the argument d psi 1 by dx is equal to d psi 2 by dx. So that way you can imagine a probability. You can imagine a crossing. You can imagine a crossing of the eigenfunction. Are you getting my point? So you can have the same story on the right hand side. Right? So the same story means if this is psi 3. So what should be important here? This psi 2 of x must be equal to psi 3 of x. And the derivative of this psi 2 of x must be equal to the derivative of psi 3 of x. Right? So this is how the problem can be solved. This is how you can obtain that finite probability that this particle will have even if its total energy is less than that of the potential barrier energy that is trying to stop it. Now, what we have in front of us is we have the wave function in 3 regions. Now, if we have wave function in 3 regions, we have Schrodinger's equation in 3 regions. And we would like to write down the Schrodinger's equation, and we would like to write down the solution of Schrodinger's time-independent wave equation to obtain the results. Right? So, for the region 1, for region 1, what is Schrodinger's equation? It is minus h bar square by 2m d2 psi by dx. This is d2 psi 1, I will call it. Okay? And plus v of x is equal to, it has to be multiplied by the eigenfunction psi of x, and this is going to be equal to e of psi of x. Right? Now we can make certain transformations here. So what we can do is, if I transfer this on the right hand side, I will have d2 psi 1 by dx. It has to be 2 here, it has to be 2 here. Okay? This must be equal to 2m by h bar square e minus v naught, I'll call it, psi of x. Now we can transfer it on the other side. If you transfer it on the other side, what you will get? You will get d2 psi 1 by dx2 plus, I will write minus v naught minus e of psi of x. This is multiplied by 2m by h bar square. This is equal to 0. Right? This is your Schrodinger's equation in the region 1. And you can write down the solution for this region. And all of you know that the solution, okay, I can boil it a little bit more. This is d2 psi 1 by dx2, then minus, I'll call it k1 square of psi of x equals 0, right? And where this k1 is what? It is under root of 2m by h bar square v naught minus e. That's it. Now what you have a second order differential equation, and you are well aware about the solutions of Schrodinger's equations in different situations, in different boundary value problems. So what will be the solution of this differential equation? Obviously, you know that this is psi 1 of x. This will be a e to the power of kx plus b e to the power of minus, there's no iota in it, k of x. This will be the solution for Schrodinger's equation. Now, what does the first term tell us? The first term is telling us to go the presence of the particle in the right hand side, and the second term in the left hand side. If I again look for that problem, what you have the first term. The first term is telling you the truth about the motion in the right direction. That means there is exponential growth in the right direction. And for the negative term, you have the exponential growth in the left direction. So, but your problem is confined to this particle in one-dimensional box, and you are interested in the boundary that is connected to the particle. You are not interested on a domain which is outside the one-dimensional box, right? So what's going to happen in that case is this term has no acceptability for our problem. So if we don't need this term is immediately equal to 0. So what you are left with? You are left with psi 1 of x. And that is equal to, come on, tell me, a e to the power of k1x. I have written it wrong then. Is it kx? It has to be k1, okay? Because I have represented that as k1. I think I committed that mistake over here also. Yeah, here is fine. So what we have is, we have this k1 of x. Now, you can see that the left-hand side of this problem is symmetrical to the right-hand side of this problem. So I can immediately think about the region 3. Region 3. So for region 3, I'll have the eigenfunction as psi 3 of x. Right? And I can write down the solution. I have used A, B. Now let me use C e to the power of k. Let's call it 3, okay, that would be more appropriate, of x, and plus b e to the power of minus k3 of x, right? Now, what you have, what you are interested, you are interested in what? You have the same problem, you have the potential, finite potential, you are talking about this region. You are interested about this direction. You are not interested about this direction, right? So the exponent that's carrying the negative will have no physical implications for us. It's not going to help us, right, in resolving the problem. So this part will exist. So if this part will exist, what's going to happen is okay, so this, maybe we are taking it wrongly. I want something that goes in the right direction. No, I want something that goes in the left direction, right? Because that is the point of interest for me. I have not something which is already in the right direction. So here, this term will be immediately equal to 0, and this term will exist. So what I'll have? I will have psi 3. Come on, tell me. Yeah, I'll have. Yeah, first I have psi 1 of x. Tell me what was that?
A.
Yeah. AE.
Or K1 of x.
It was K1 of x. Okay. Now I have psi 3. And what is psi 3?
D power minus.
Is it D?
Minus.
D e to the power of minus K3, sorry, K3 of x. Alright? Okay. So now we have the middle one.
Second.
And middle one we are very well aware about. Okay? So the middle one I will call psi 2. Now psi 2 of x will be what? Psi 2 of x will be A, B, C, D is gone. Now I will call this e to the power of I, kx, this is 2 now, plus f e to the power of minus I, k2x. Right? Clear? You have a particle in the middle of this defined one-dimensional potential. And here, this solution has come for what? It has come from Schrodinger's equation. And what is the Schrodinger's equation for this region? It is, yeah, minus h bar square by 2m d2 psi 2 by dx2 plus v of x is 0. I won't write that, okay? So is equal to e of psi 2 of x. This is your Schrodinger's equation, and this is the solution for this. Okay, so let's continue on. Okay, so what we have now, we have here 2m by h bar square e psi 2 of x equals 0. So here I'll have the differential equation d2 psi 2 by dx2 plus, that was k1, k3, this is k2 square of psi 2 of x. Okay, so now what we have? We have the three equations, okay? And we certainly want a connection. We want a connection between the equations because only then psi is having some applicability. Psi is having its own importance. So can you tell me the first equation? Yes, Imran? Yeah, psi 1 of x
is equal to
a e to the power of
K1 of x.
k1 of x. Okay, this is psi 1. Okay, psi 2, no, psi 3, you tell me psi 3.
Psi 3 of x is equal to
de minus
K3 of x.
k3 of x. Fine. So you will have now psi 2 of x. And what is that?
E.
That is e to the power of I,
K2 of x.
k2 of x, okay? Plus f e to the power of minus I, k2 of x. Now see, this one is the eigenfunction of the particle being inside this one-dimensional box. And you know that the solution of this problem will lead us to odd solutions and even solutions, right? So I can think of this solution in terms of even function and in terms of the odd function. So for example, cos of x, what is it? It is odd function, and sine of, no, cos is even function and sine is odd function. Okay, so how can I tabulate it? Now what I have for potential, I have three regions. The first one is V0, another is 0, another is V0, and the first one is for x is less than minus L by 2. right? And for the second, x is between minus L by 2 and L by 2. For that region, the potential is 0, and it's again V naught for x greater than L by 2. This is one way of doing it, okay? Now, looking for the solution. Now, looking for the solution. How will you expect the solution, psi of x? You will have two types of solutions. One will be even solution, because the eigenfunction that I wrote down for the middle region, it contains both even and odd solutions. So we will have to break that solution. So psi of x will be what? It will be, okay, it will be a e to the power of k1x. Okay, what was here? This is e. I will call it e dash. I'll call it f dash. Any problem? No problem. Because then you will have another constant. I will write down that as e. So here I will write e cosine of k2x. Okay, and the third solution will be what? D e to the power of minus k3 of x. Right? So this will give you what? Which solutions? Yes? It will give you the even solutions. Because cos of minus theta is cos theta. Right? So this is the solution that will fall in the framework of even solution. Now, do you remember the even solution? What was that? It was, if I move the right hand, say 1 meter, I have to move the left hand, same 1 meter, but in the opposite, in the opposite direction, right? But with same geometry, with same symmetry, right? For odd, what you have, if I raise my hand, another hand will go down. So this solution that we have written is what? It's the even solution of our problem. And there will exist the odd solution also, because you will find that you will have alternate even odd solutions. So here, what you will have, psi of x will look like what now? It will be a e to the power of k1 of x, and then f dash. So f dash I will now boil down to f. So this will be f sine of k2x, and then d e to the power of minus k3x. Fine, okay? So we have decorated it, and now after this we will have to go with the boundary conditions. We have to resolve the boundary conditions to make a plausible solution of this problem. So I will stop here in this case today. We will proceed on this from here tomorrow. But before we end this talk, we have already gone through the problem of particle in one-dimensional box. Now, I have a problem for you which you will solve. Okay. So the problem is that you have a one-dimensional box, and the length of this one-dimensional box is 6.6 times 6.6 nanometers. Okay, it carries a particle, say electron, and the mass of electron is 9.1 times 10 to the power of minus 31 kilograms. So my question is that what will be the allowed energies for this particle for the first three states, right? For the first 3 states, how will we calculate this? You must have gone through that particle in one-dimensional box problem, infinite potential box. Okay, how will you solve this problem? Come on, look at me. So For that, what you have the energy. And you calculate that energy is how much? That is n square h bar square pi square by 2ml square. This is the energy. These are the allowed energies that can be given to this particle that are dictated by these infinite potential walls. So I want you to calculate E1, I want you to calculate E2, I want to calculate E3. So simple. Okay, so how can I write down this problem now? I can write down this problem as, say, E is equal to n square. Okay, n square. For h bar square, I will write h square by 4 pi square. Then you have your own pi square here. And then you have m l square. And you have 2 also. So this bar will go because I'm taking this reduced Planck's constant in its original form. H is equal to, h bar is h by 2 pi. So what's going to happen here? So you will have pi square and pi square will go, right? So 2 4s will give us 8. So E will be n square h square by 8 ml square. So this will be our boiled down equation for energy. So we would like to calculate this. So how can we calculate? So E, n, this is basically n. I will keep n square as it. So what will be inside? See, I have given the easiest one so as to resolve this problem. Okay, so H is, that is 6.63 into 10 to the power of minus 34 joules. But I will take only up to 1 order. So it is 10 to the power of minus 34 times 6.6 times 10 to the power of minus 34 divide by 8 is there, okay? Okay, the mass of the electron is 9.1, but I will take only 9. 9 times 10 to the power of minus 31. Okay, then you have 6.6 whole square. Nanometer means 10 to the power of minus 9. So this is 10 to the power of minus 18. Are you getting? Okay, so if this is done, what you are left with? So you are left with n square. You can see this 6.6, 6.6, and the square of this will cancel. Okay, so you will have 10 to the power of 4 plus 4 will give me 8, 3 plus 3, this is 10 to the power of minus 68, right? Divide by, this will be 72 times 10 to the power of, this is 1 plus 8 is 9, and 3 plus 1 is 4, this is 49, minus 49. Now you will take this out. So minus 49 will become plus 49. So you will have En equals n squared. Yeah? It is 10 to the power of minus 68 times 10 to the power of plus 49. Okay? Divided by 72. That's it. Joules. Right? Any other number? No. So this is n squared, and this is 10 to the power of minus 19 divided by 72. But what is it? It's in joules. I want my answer in electron volts, right? So in order to convert this into electron volts, we will divide this by 1.6 into 10 to the power of minus 19. So what you will get? You will get E equal to En equal to n squared times, okay, yeah, 10 to the power of minus 19 is in the numerator, okay? In the denominator you have 72 times 1.6 times 10 to the power of minus 19, but it has transformed into electron volts, right? So 10 to the power of minus 19 and minus 19 will go. So what you are left with? You are left with En equals n squared times 10 by 72 into 16. Okay, but what? Electron volts. Clear? Now you can multiply this and you can get answer in 0.00 kind of electron volts. For the first, n will be given by 1. For the second, it will come as 4. For the third, it will come as 9. So this is how sequentially you can calculate the allowed energies for this particle in this one-dimensional, in this one-dimensional infinite potential well. But we started with the problem of one-dimensional potential well, in which the potential is finite for the particle, and we are trying to calculate that does this particle has any probability that this particle can cross the barrier, which is impossible in classical domain. And for that, the argument that I gave is that this particle is treated as a wave function inside the box. So wave function means it's not a ball, it's not a tense ball, it has a spreading nature. And this spreading nature, you will see, it gives this particle a tendency to tunnel. It gives it the tendency to leave this finite potential barrier. Okay, any questions?
No, sir.
Okay, I thank you all.